This is problem 4. A rigid beam AB is supported by a steel rod and an aluminum rod. So this is a steel rod, all the properties are given, area, length and elastic modulus. Similarly, this is an aluminum rod, A, L and E are given. A load P of 675,000 kilonewton, 675 kilonewton is applied at A. What will happen to this? It may probably deflect like this. So what is done is, now the screw at B is adjusted such that it brings this down so that it is horizontal. Okay, it's an interesting problem. There are two problems in this. One is the stage when there is deflection, deflected. The other is set horizontal. The initial condition is that it is horizontal and there are no forces on this, assuming that there is very less weight due to this. And this is a rigid bar. So these are the information that we have already. How do we go about it? Let's look at the first case, which is the deflected case. What do we have? We have this. There is a force offered by the aluminum rod. We'll call it as, let's say, F aluminum. Let's make this as CD. So this is FD. And the resistance offered by the steel bar is, let's say, FC. The force P is acting over here. And this is in equilibrium. There is a deflected shape to it. First, let's look at equilibrium. There are two unknown forces due to the force P. It's possible for us to find out both these forces from equilibrium equations. Sigma Fy equals 0 and sigma M, we can choose one of the points. For example, like we can choose point D in order to get the value of Fc. We can also choose point C to get Ft. But basically from equilibrium equations, it is possible for us to find out both these forces. Once we find out the forces, we will use the material property. We have this steel available, steel elastic modulus available, aluminum elastic modulus available, and the appropriate dimension are also there. So it is possible for us to find out the stiffness of the steel bar to be equal to E of that steel bar times the area of that divided by the length of that. Similarly, it is possible for us to find out for the aluminum bar, which is EL AL by LL. We will call it as EAL. Force is given, stiffness is known. Can we find out deflection? The answer is yes. So in order to find out from the original condition, which is this, what is this deflection and what is this deflection, we will use Fc and Ft. So that, let's call this as delta C and delta D. Delta C equals Fc by Ks, delta D is equal to Fd by Ka. Right? Now, using this, it is possible for us to find out the equation of this line. And therefore, it is possible for us to find out what is this deflection. Let's call this as delta at B. So let's say we'll call this as delta B. So we can find out from this geometry delta B. The next task is to make sure that this screw is pushed below make it horizontal. So let's take the configuration related to setting it to be horizontal. So in order to make a distinction, we'll call this as delta B1. Let's move to the next problem, which is the problem number 2. Okay, now in problem number 2, what we have is the free body diagram. So in the problem number 2, or the problem related to the setting horizontal, we have again a resistance from this. Let's call this as F2C, and resistance from the aluminum rod as F2D. But we also have the screw providing some reaction. Okay. For consistency, we'll just put it in the same direction. We'll call this as FB. This was not existent earlier. This force P is also acting here. Remember, from this we have 3 equations that we need to know in order to be able to find out these 3. But we have only 2 equations, sigma Fy equals 0 and sigma M about one of these points, A, B, C or D. Let's just take it as, let's say, sigma M at A is equal to 0 as the 2 equations that we can get, which means we have insufficient equilibrium equations to solve. What do? We have to invoke God, geometry of deformation. What does the geometry of deformation says? It says the moment of delta, the moment at C will be the same as moment at D. So delta C should be the same as delta D. Now we already know the stiffness of this and stiffness of this, so we can write this to be the force 2 at C divided by Ks, which is nothing but delta C. That should be equal to Ft2 divided by Ka. Right? So this provides us the third equation apart from these 2 equations. And therefore, it's possible for us to find out the Fc2, Fd2, and this particular screw reaction, let's say Fb. Back calculating, it is possible for us to find out what is delta C, which is nothing but Fc2 by Ks. Similarly, which is nothing but delta D. Now, how much has B moved? The same extent. So let's say this is delta B. So from the horizontal position, it has again come to the horizontal position in this particular case. So the total deflection that has happened from the initial state to this is equal to delta B2. Now we have solved these 2 problems. Let's look at the whole thing as a whole. So we had the first one, which is the deflected shape. So this is the original. It has depressed a little bit, and so this is the initial state. This is the deflected state, and this is the set right state. So let's just call that a set right state, where we pushed this to a certain extent. Now, from this to this, there was a deflection, and from this to this, there should be a deflection. Okay. This we found out from the second one, which was delta B2. This we found out from the first one, which is delta B1. The difference of these 2, which is delta B2 minus delta B1, is the extent to which I have to push this to make it horizontal, and therefore this is the descent that screw should make. I hope this is clear to you. Okay, so it's an interesting problem.